రికార్డింగ్ ఆపేయండి. ఇప్పుడు రికార్డింగ్ ఇప్పుడు వద్దు. గుడ్ ఈవినింగ్ ఆల్. వెల్కమ్ టు ద FDP third day session 1. So today we are glad to have our keynote speaker Dr. M. Sabarimalai Manikandan, Associate Professor, IIT Palakkad. I'm going to give small introduction regarding our today's keynote speaker. So Dr. M. Sabarimalai Manikandan received BE degree in ECE from Bharatiya University, India, and ME in Micro and Optical Engineering from Madurai Kamaraj University, PhD degree in Biosignal Processing from IIT Guwahati. He was an assistant professor in July 2013 to December 2021, IIT Bhubaneswar, and Sara is also Chief Engineer with Advanced Technology Group, Samsung India Electronic Private Limited. Sara was an assistant professor at Center for Computational Engineering and Networking, Amrita University, and lead engineer from January 2009 to January 2010 with Audio Group, Samsung India Electronic Private Limited, Noida, India. So the main research focus of our keynote speaker is, I'm glad to announce that, which is very aligned with our topic, our theme of the FDP, that is design and development of energy efficient AI powered health sensing and monitoring systems, which is very relevant to our theme of the FDP. Sir, professional activities and recognition awards, sir, is the recipient of the 2020-2012 Outstanding Performance Award, and also Employee of the Month during his tenure at Samsung India Electronic Private Limited. Sir received 2019 CVET Most Cited Article Award at the Biomedical Engineering Society Conference. He is currently the chair of Cardiorespiratory Subgroup of IEEE Standards P1752.2 and Vice Chair of Working Group of IEEE Standards P2520.3.1. Sir was also member of Working Group of IEEE P1924.1. Like, sir is also technical expert committee member and project proposal reviewer for SAR, DSP, DST, and various funding bodies. Sir is also having institute administrative responsibilities in various positions. We are glad to have such a great personality as a keynote speaker for our FDP. Thank you very much, sir, for accepting our invitation and you presentation on AI in predictive analytics for healthcare. Thank you very much, sir.
Thank you for the introduction. Can you see my slide in full screen mode?
Yes, sir.
Yeah. So if there is any interruptions, please inform me. and also please mute your all mics, okay, to avoid disturbance while presenting. So yeah. So just as per the title, artificial intelligence in predictive analytics for healthcare. So here we have three aspects. One is a healthcare application. Hello, is it audible?
Yes, sir. Balakrishna, unmute all other participants. Balakrishna is there? Okay, sir. Thank you, sir.
Yeah. So three major aspects we can see from the title, that is healthcare. But if I see the title of FDP, AI innovations in healthcare and medical technology. So here healthcare is most important applications for artificial intelligence. And in particularly with the help of artificial intelligence, we are trying to do some predictive analytics. So we'll see what are the different types of big data analytics and what are the challenges when you want to develop descriptive analytics, diagnostic analytics, predictive analytics, and prescriptive analytics. So in all healthcare applications, we must know the basic concepts of artificial intelligence, big data analytics, Internet of Things, cloud computing, and also signal processing. So with a few examples, I'll try to highlight the importance of signal processing with a combination of a deep learning networks where we can reduce the overall computational complexity or a model size without compromising the accuracy and reliability. So if you look at any automation technology, or we can say wearable health devices or medical devices, we must focus on the limited battery capacity. That means how do you reduce the overall energy consumption of a system so that the developed algorithms, or we can say the proposed device, can be used for continuous long-term health monitoring. Then computational speed is very important to timely take the treatment by processing large amount of data with the support of your deep neural networks. Then we have to deal with the limited wireless data rate, but that's not a research problem nowadays because we have a low power, high data rate wireless radio. But however, if you are transmitting huge amount of data, still we have to consider how much the energy consumption at the wireless level or wireless radio level. Now, to briefly summarize, we have a broad vision, or we can say research goal. It's called automation, which includes control and monitoring. So control will have a different kind of challenging problem. In the sense, I'll estimate some parameters, and based on the outcomes of that device, I'll control the function of the other device. Maybe with the intervention of or we can say with and without intervention of a human. In this case, we expect that the control action should be without intervention of a experts. For example, if you measure the blood glucose level by using non-invasive sensor, based on the level of the blood glucose, we should be able to control the function of the insulin pump, okay, which will be operated without intervention of a human or expert. But if you take a monitoring application of a healthcare domain, it may be some kind of event detections or event classifications or event predictions. Let us take a cardiovascular disease. So at the initial stage, or we can say at the first stage of the cardiac health monitoring, we must detect a normal and abnormal patterns. It can be a detection problem. Or I can say that we are trying to detect any specific type of events. Let us take QRS complex, which is most prominent in the ECG. If we can detect the location of the R peak, I can derive the RR interval, which will be used for heart rate variability analysis. So this is called a detection problem. The detection problem will have a different challenges as compared to a classification system, or we can say event prediction system. So in this case, if I consider a event classification, once we know the various kinds of, or once we detect the abnormalities of your heart functioning, then we can have variety of cardiac arrhythmias. So it will be related to arterial cardiac arrhythmias, ventricular cardiac arrhythmias, which includes premature ventricular contraction, ventricular fibrillations, ventricular tachycardia, arterial fibrillations, arterial flutter, then left atrial enlargement, right atrial enlargement. So these are the different types of cardiac events, which can be a classification problem. Now, if we come to the event prediction, which is most important for any kinds of a health monitoring applications, it's not only for a human, it's also for an animal or a machine or a structure. So we must know, we must predict a specific type of disease or abnormalities so that we can reduce the risk factors. If I can reduce the risk factors means I can save or I can extend the lifetime of the function of the heart organs, or we can say we can reduce the overall cost, or we can say we can improve the productivity of any kind of machine health monitoring. So in this case, heart monitoring. So let us take the examples of a premature ventricular contraction, which is one of the one type of ventricular cardiac arrhythmias. So where when we fail to diagnose PVC, premature ventricular contraction, we can see a presence of ventricular tachycardia. So if the ventricular tachycardia is not timely treated, then we can see ventricular fibrillations. So now we can see the what is called sequence of events. So we'll do detections to know whether it's normal, abnormal. Then we do classifications, and then we'll identify a specific type of cardiac arrhythmias. Then we'll apply prediction, then to know the or to predict a specific type of life-threatening arrhythmias. All these applications, for example, event detection, cardiac arrhythmia, abnormal detections, cardiac arrhythmia classifications, or cardiac life-threatening arrhythmia predictions, we'll use deep learning networks nowadays, or we can use traditional machine learning classifiers with the what is called application-specific feature extraction techniques. So these are called AI-based event monitoring applications. Now, what is the smartness? What is the intelligence? Now, since we started with the use of AI tools, or more particularly deep learning networks, to improve the accuracy and reliability of automated cardiac arrhythmia prediction system, cardiac arrhythmia classification system, or automated cardiac abnormal detection system. It's our automation. So for improving the accuracy of automation process, also need a selection of a suitable signal processing deep learning networks. And also we have to consider the energy consumptions, because most of the wearable devices are restricted with the limited battery capacity. Now, what is the smartness here? So here there is no smartness. We are just trying to improve the accuracy of your detection system, or we are trying to improve the accuracy of a classification system, or we are trying to improve the accuracy of the prediction system. Now, whether this type of parameters are vital signs which are extracted from a biomedical signal will be suitable for specific type of diagnosis, that depends upon the contextual information. For example, you consider the wristwatch. Okay, so we can say it's a digital watch. It's not a smart watch, because it has a set of sensor, and each of the sensors are used for specific type of parameter extraction. Let us take a PPG sensor, which is used for measuring the pulse rate. Sometimes we are using PPG sensor to measure the respiration rate also. Sometimes we are using PPG to measure the blood glucose level in a non-invasive manner. Sometimes we are using PPG sensor to measure the coupler's blood pressure reading. So it is going to, it means that PPG sensor is used for extracting a specific type of vital sign parameter, or we can say vital parameters, including a pulse rate, respiration rate, blood pressure, blood glucose level. Now it is called automation. How much accurately we can estimate in the presence of various kinds of noises and artifacts. That is a challenging problem. Maybe the algorithm can provide accurate estimation of these parameters under resting conditions, but may not produce reliable parameters under what is called ambulatory conditions and the exercise conditions, where we can see the presence of noise and artifacts. Now assume that the parameters are accurately estimated by using a wristwatch, which is enabled with the symbol signal processing techniques. But whether that estimated parameters useful for diagnosis or not, or we can say it is a clinical grade, or we can say medical grade, whether it's useful for not, useful for clinical studies, or it cannot be useful for clinical studies. So now let us take the examples of pulse rate variations. So the pulse rate can be varied, or we can say you can see the variation of the pulse rate under different emotional conditions, under different physical activity conditions, under different weather conditions, under different what is called extreme heat or extreme cold. Now, do we have such information with the wristwatch? We do not have. Now, we cannot say that that is a smart watch. It's just a digital watch. It can provide or it can automate the process of estimating the vital sign. Whether that vital signs can be used for clinical study under resting conditions, ambulatory conditions, or in a remote health monitoring applications. So now if you consider remote health monitoring applications with the use of wristwatches, if that watch is not enabled with this type of contextual information, then we cannot say that these are the smart watches, or we cannot say these are AI watches, or we cannot say this is an intelligent watch. It is just a process. It has a set of signal processing or deep learning networks to automate the process of estimating parameters with the high accuracy and reliability. So that's why we must know these three terms: automation, which includes control and monitoring, which can be solved with the traditional signal processing and machine learning, and also which can be solved with deep learning networks. And then we must know what in by smart watches or smart devices or intelligent devices or intelligent watch, or we can say AI medical devices or AI powered medical devices. If I say AI powered medical devices, I should have a good automation technology and also intelligence protocols. So what we have nowadays, or what we have seen in the research study, most of the times they have a good automation technology to accurately estimate the parameters, but they do not have a intelligent protocols, what I explained with the example of a pulse rate estimation. So therefore, we must know all these terminologies called event monitoring, target monitoring, and biometrics. Now, what is the smart healthcare system? How do you say the given healthcare system is a smart? Because I take an example of wristwatch. It's just a digital watch which cannot be a smart watch or a AI powered watch. So now we have a set of sensors, and then we will have a data acquisition system. So could you please mute your mic? Excuse me. Yeah, ma'am. Saraswati ma'am, please mute your mic. So we have a data acquisition system which operate with a different sampling rate, that depends upon the type of signal to be processed. So let us take a cardiac signals. You have electrocardiogram, you have phonocardiogram, you have photosplissomogram. Then if you take a brain, you have electroencephalogram. If you take your muscles, you have electromyogram. Then if you take again seismocardiogram, then ballistocardiogram, then each of this what is called signal will have a different bandwidth in terms of what is called frequency range of a signal. Now, based on this frequency range of a signal, we'll choose a sampling rate. And that sampling rate can be selected depending on the application also. I can again take the example of what is smartness in the device. Let us take a PPG sensor used for measuring only a pulse rate, which is adopted in the most of the wearable devices or wristwatches, where we must know what is the range of the pulse rate. If we do not know this information, we cannot provide an innovative solution in reducing the overall energy consumptions and improving the what is called the accuracy and reliability by reducing the false alarm rate. That's very important. We have to reduce the overall energy consumption and also a false alarm rate. In the sense, we are improving the accuracy and reliability. Now, if I say that I want to develop a smart watches or a AI-enabled medical devices, I must consider a variety of data, in the sense contextual informations. Like the data comes from the accelerometer, which will be used for predicting the activity of a person who is wearing the wearable devices. If I should have some emotional sensor, I should have some air pollutants sensor, I should have some ambient sensor. So which cannot be done, what is called with the existing wristwatches, which will increase the complexity of the device, or we can say we increase the what is called the size of the device. It will be bulky. Instead of that, I can explore existing this type of environmental sensors by integrating with the Internet of Things. So while transmitting my pulse data, I will also sense a data from a existing network, it may be internet protocol network. So then we will try to process with the signal processing. Without signal processing also, we'll try to do all information extraction by using deep learning. But I would like to highlight here that if you use signal processing with the deep learning, or I can say the signal processing empowered deep learning network can provide better accuracy and reliability with reduced model size. I'll show a few examples. Why do you want to highlight still, or why do you want to use a traditional signal processing? Still, you can improve the deep learning, or we can provide some kind of a explainability here. Otherwise, we'll produce some kind of features, then later we'll try to use some kind of model to explain the proposed model. So these are the things we have to consider when you want to develop a AI-based health monitoring system. Now, as we know that signals are everywhere, since today presentation is with the focus of healthcare, so in a human body, you will get a variety of signals and images. Now, if I do not understand the characteristics of the signal to be sensed, to be analyzed, to be transmitted, okay? Why do you stress sensed, processed, and transmitted? Because sensing can reduce some amount of energy consumption. If I select a sampling rate based on the parameter to be extracted, I can reduce a significant amount of energy at the sensor level, or at the sensing stage, or at the sensing model. Now, this is called a fundamental knowledge. This is called science in a data. That means I know what type of parameters that need to be extracted for the diagnosis of specific type of disease. Now, I know for that parameter, this will be the required bandwidth of the signal. Then I can choose a suitable sampling rate, which is not adopted by many of the research group. They just collect the signals, and even they say that they are going to do only heart rate variability analysis, or they say I'm going to detect only particular type of life-threatening arrhythmias. Then still they use the entire spectrum of the signals, which may not be required for a specific type of application. So this is called fundamental subject, some fundamental knowledge at the sensing level. So that's very important. So here I want to highlight that or any AI engineers or researchers or so-called data scientists, they have to process only signals. It may be a one-dimensional signal, it can be a two-dimensional signal, or it can be a video. Hello, please please mute your mic. Yeah. So I just give some glance of your signals. We can see signals: ECG, PPG, SCG, BCG, ICG, GSR, EEG, EOG, ERP, EMG, VAG, VMG, EGG. We must understand the characteristics of the signal. Characteristics in the sense, we must know what is the temporal characteristics and spectral characteristics. Without knowing these temporal and spectral characteristics of the signal, I cannot be a good data scientist. Because the data scientist in the sense, intelligent data scientist in the sense, they aims to provide an innovative solution with improved energy efficiency and false alarm detections. That's very important. So this is the energy consumption reduction and false alarm detections requires the basic subject, or we can say basic concept of the temporal and spectral characteristics of the signals. Similarly, we have different kinds of sounds which can be sensed from the human body, and there are 4 types of what is called application scenarios. One is body-worn devices, smartphone-based applications, IoT cloud-based health monitoring, and clinical decision support system. Now, this is very important slide. I can say again, significance of your fundamental knowledge. Again, if we say data, if you want to be a good data scientist in developing a AI-based healthcare prediction system or what is called a healthcare analytics system, I must know that what are the vital signs parameters that we are going to extract, which is most important for diagnosis of various kinds of diseases. So we have heart rate, we have respiration rate, blood pressure, oxygen saturation, and body temperature. I must know what is the normal range of each of the vital signs. So 60 to 100 beats per minute, 12 to 18 beats per minute, and then blood pressure is 90 per 60 or 120 bar 80. This is called systolic blood pressure and diastolic blood pressure. The down is a diastolic blood pressure and the upper one is the systolic blood pressure. Then oxygen saturation is a SpO2, which is 95% to 100%. Then body temperature is this. Now, why do you want to know this? Without knowing this, I can do everything with the deep neural network. That is our argument. Yes, you can do, but you have to still explain the models. That's called explainability, they say. But if I know this one, if I consider this information while generating the model, or you can say to train the models with less number of parameters without compromising accuracy. So now, if I take examples of pulse rate, so here the normal range is 60 to 100 beats per minute. But since we are going to develop a system for human healthcare monitoring, I can know what is the pulse rate range for a human. I can have a pulse rate range for animals. I can have pulse rate range for some other what is called any kind of animals or any kind of birds. Now, in this case, if I consider human, it is 30 to 300 beats per minute, which can be seen in most of the commercially available multi-parameter monitors. So that is a reference for me. That is called 30 to 300 beats per minute. Now, what is the equivalent frequency range of a 30 to 300 beats per minute? It will be equivalent to 0.5 to 5 hertz. Now, the pulse rate frequency range is 0.5 to 5 hertz. Now, my objective is to develop a smart watch, or we can say wristwatch, to display only the pulse rate. Okay. So, in this case, instead of sampling a signal, PPG signal, with a rate of 100 samples per second or 125 samples per second, which is followed for many kinds of PPG-based cardiovascular disease diagnosis. And I can use only a less number of samples because my pulse rate frequency is from 0.5 to 5 hertz. I can, according to the Nyquist theorem, I can choose a 10 hertz, or you can say 10 samples per second, or to have better time resolution, I can choose 25 samples per second. So this is adapted in most of the innovative devices. Okay, it's not intelligent devices, but here we are reducing the energy consumptions by choosing a suitable sampling rate, by considering the specific parameters that need to be extracted and transmitted to the cloud or transmitted to the expert. So 25 samples per second, that means instead of using 100 samples per second, that is adapted for different kinds of diagnosis, I can use only 25 samples per second. That means 5 times I can reduce the power consumption. So that is called intelligent part of the engineer, or you can say data scientist who can choose a suitable sampling rate and they can reduce the overall energy consumptions in the parameter extraction stage, okay, by reducing the number of samples. So this is one of the example. You can apply for respiration rate. You can apply for any other parameter extraction approaches. So therefore, this slide is most important. If any data scientist who wants to work with the healthcare or you want to be expert, if he does not know this type of information, he cannot provide any innovative solution. He also just do with some kind of deep learning. It will produce a large model for even for extracting the pulse rate, which can be done with a simple signal processing and which can also be a best energy efficient pulse rate estimation technology for most of the resource constrained wearable devices or resource constrained portable devices. Now, we must also know what are the different applications of this type of wearables. So sometimes we'll extract the physiological parameters, sometimes we'll extract the fitness parameters, sometimes we'll extract the parameters which will be used for mental states. But here itself, we can find a confusions. I'll show one of the slide where the most of these devices, whatever the devices which will be used, need some contextual information also. I'll show that without contextual information, we cannot do any further diagnosis based on this type of vital parameters, even if it is estimated accurately and reliably. Now, we must also know that what are the different kinds of parameters that you can extract. Let us take one good example of cardiovascular disease, or we can say diagnosis of heart disease. So we always see an electrocardiogram. It reflects the electrical activity of the heart. Then we have a phonocardiogram. It will reflect the mechanical activity of the heart. We will have a heart sound up, down, and also heart murmurs. Then we have photoplethysmogram, which reflect the blood volume, okay, or we can say circulatory activities. So blood volume, but which is used for what is called measuring the pulse rate. Now, each of the signal will have a different patterns in the time domain. Now, look at the electrocardiogram. Then you have ECG. In that ECG, that is, you have P wave, QRS complex, and the T wave. Each of these local waves is the example of mixed waves. A single ECG signal, or you can take a single cycle of ECG signal, we will have three major local waves: P wave, QRS complex, and the T wave. This is a sequence of your local waves. It will be repeated. It will be repeated. Now, when I say it is repeated, then I can say it is an example for cyclostationary. That means the cycle pattern is repeated, then it gives some other information. That information can be used for selecting a suitable deep learning networks or signal processing techniques. I'll show one of the example for a cyclostationary signal processing. So in this case, you have P wave, which reflects what is called a contraction of the arterial chambers. Then you have QRS complex, reflects the contraction of the ventricular chambers. Then you have T wave, it reflects the relaxation of the ventricular chambers. Now, each of these actions, we have P wave. The P wave is defined with some set of morphological parameters: the duration of the P wave, amplitude of the P wave, and shape of the P wave. And similarly, QRS complex. Then similarly, you have T wave, amplitude, shape, and the duration. And in between, you have some kind of a segment. It's called intervals, PR interval, or we can say that PT, what's called PQ interval. Then we have ST segment. ST segment depression, ST segment elevations. Now, if I can develop a simple signal processing techniques which can detect the onset and offset of each of the local waves and also the peak of the local waves, then I can able to do the diagnosis of various kinds of heart disease, which is well adopted by the doctors or in the clinical laboratories. Is it clear? So, because each of these disease, particularly a disease related to arterial chambers, are defined with the amplitude of the P wave and the shape of the P wave and the duration of the P wave. So, similarly, you have narrow P wave, tall P wave, and wide P wave, and notch in the P wave. Similarly, QRS complex also, narrow QRS complex, wide QRS complex, T wave also symmetric, asymmetric, tall, and inverted. So, each of these morphological parameters defines or reflects the malfunctioning of the specific portion of the heart. Okay. So now if I can do this type of what is called delineation process. What is delineation process? Is the process of estimating all these parameters. Then I can use those parameters for diagnosis of various cardiovascular diseases, which is possible. Still, we can able to solve if the signal is a noise-free signal. But if it is a noise signal, there are many challenges. Now, we are expecting that deep learning networks can capture this type of peak amplitude ratios, durations, then segment interval, and wave area and wave area ratio, then some kind of what is called shape features, including narrow and wide. Now the question is, who is going to create a database by considering all kinds of cardiovascular diseases or cardiovascular or cardiac arrhythmias to develop a deep learning based cardiovascular decision system or decision making system? So we have a brain network, or we can say deep learning networks. We have a HAI accelerators. But who is going to create a database? That's a challenging problem in this research, because you have to consider the possible variations of the P waves and where to create a possible variation of the P wave, because different age group will have a different amplitude range. But if I can develop a ECG wave from delineation, still I can solve the problem of cardiovascular disease irrespective of the ages and genders. But if the deep learning, if I want to use it, then I must give more importance to creating a variety of data or possible variations of the P wave, QRS complex, ST segment, T wave, and that's such a challenging problem. So that's why we should know how do we say that a deep learning based cardiovascular disease prediction system based on a specific database may not be that model may not be suitable for various kinds of this. So this is the example. We can see that some of the devices will display arterial fibrillations, and these are the different what is called sensing site. This is also a fundamental knowledge. If without knowing this one, I cannot say that whatever the model which is derived, okay, can be used for a PPG signal captured or sensed from the ear loop, a PPG signal captured from the fingerprint. Please mute your mic. Please mute your mic, ma'am. Yeah. So now, so in this case, we must know that this model is created irrespective of the sensing site. That means what? Sensing site also will define the quality of the signal that will be captured. The fingertip will be will produce a high quality PPG signal, but it is more disturbances for the users who are individual, who daily involved in many kind of workload and daily activities. But if you take a ear loop sensor, which is more comfortable for the an individual who is having many kind of activities or workload in a day, but it can produce a poor quality. So this information we should know that. So what type of quality of the signals that we can get from each of the sensing site. Now, when I say that I'm going to integrate my physiological parameters with the surrounding parameter, or we can say physical activity parameters, emotional parameters, and environmental parameters, then we must give importance to the Internet of Things. So I briefly introduce the concept and architectures and key challenges of the Internet of Things. So this is a brief summary that you know that we started the network, internet, mobile internet, mobile plus people plus PC, then Internet of Things. Then we also seen device-to-device communications, device-to-machine communication, Internet of Computers, wireless sensor networks, machine-to-machine communication, cyber-physical system, Internet of Things, and Internet of Everything. So sometimes I use this word. It's called, these are the fancy words, because so we are talking about Internet of Things, but nowadays other people are talking about Internet of Everything. But the complex, but the basic problems that need to be addressed, that okay, ensuring the communications reliability and network coverage, which is most important. Is it possible to get a data, contextual data, at the time of processing or at the time of sensing? At the time of sensing, I do not have what is called perfect networks. Then how do you compensate that contextual information when you want to use a symbol or when you want to use a vital signs for the diagnosis? So these are the challenging problems. We have framework, but the challenges are how do you address the communication failure? Who will provide a network coverage? When I say that I want to sense a health of a person who is living in a remote location, it's a very interesting statement, but the challenges are who is going to provide a network. That network is going to give a connections between the remote or remote individual or a remote patient to the doctor. That's very challenging problem. You can implement remote health monitoring in a urban area, or we can say that in a city where we have a perfect connection, but still within a home itself we will not have a perfect connection. So these are the many challenges that need to be addressed when you say that I'm going to work with the Internet of Medical Things based AI based system. But Internet of Medical Things is most important. It will empower this AI based prediction system, because AI need a wide variety of data in terms of contextual parameters. Who is going to provide? Internet of Things computing platform, because which can integrate a heterogeneous sensors which operate with a heterogeneous radios also, because that depends upon this. I have heterogeneous sensor means it operates with a different sampling rate. I must have at least 2-3 radios where one radio will fail, but other radio at least it will work. So heterogeneous wireless radios. So it may increase the cost, but it can ensure the some kind of a communication reliability, because it operates with a different frequency range. So that's why we must know that we should work with their lightweight wearable device technology, including identifying intelligent sensors, low power sensing circuits, low power signal processing techniques, and low power high data rate wireless communication or wireless radios, and high speed processor. Now, I'll just briefly introduce wireless sensor network, because it's also just a fundamental concept for IoT. If you can understand this one, the IoT problems can be also solved, because what we expect that many things will be integrated by using any kind of your wireless networks or wired networks or combination of wire and wireless network, which can control the function of the other devices or which can control the function of other things or other object without intervention of a human. That is the expectation of this IoT based application. But how to make it possible or feasible, that it has that needs many research problem to be solved. So in this case, what I say that I have some kind of insulin pump. Okay, I have a blood glucose monitors. So it will continuously monitor or it can monitor the level of the blood glucose. Then based on that, it can control the function of the insulin pump without intervention of a doctors or without intervention of a experts. So in this case, that we can say that they are connected with the wireless networks. So like this, we have many things actually. So many things means body centrics. Okay, you have many wearable sensors, and it can, for each of the sensors monitor the function of each some of the specific type of organs, or we can say vital organs. Now, one function of one organs can be controlled based on the parameters which are monitored with the other organs without intervention of a human. So therefore, we must know what are the specific requirements of wireless sensor network, which can be extended for our IoT platform also, that we can say specific requirements of IoT or Internet of Medical Things or Internet of Health Things, which is called reliability, latency, and security and power consumption. Now, when you say that your device is connected with the internet world, we must ensure the security. So when you say that we are going to do processing at the edge level or a cloud level for extracting the vitals and parameters, then we must know that latency. How do you address the latency? Because we have to timely control the function of the other devices or other things. Then reliability is very important, that whether this data is reliable in terms of the quality is also very important. Whether the parameter which are extracted by using algorithms, okay, it's a reliable. But in this case, we can say reliability of the communication network. So now, for any kind of smart automations, we are going to use Internet of Things, signal processing, some intelligence which are derived from various kinds of contextual data by using deep neural networks. Then so this is also a brief summary of this. What is IoT? That means it create, communicate, aggregate, analyze, act, which is called information value loop, which is also, I can say, vision document. Each stage has a different problem. Create is very simple. The use of sensor to generate the use of a sensors to generate information about the physical event or any kind of organs. But when you say use of sensor, who is going to design a sensor? It should be a lightweight sensor. It should be a high sensitive sensor. It should produce a high quality signal. But when you say I'm going to miniature a sensor, then we should check the quality of the signals. If sometimes the sensor is bulky, but still it can produce a good quality of the signals. But if the sensor is very small, which is very much bound to the movements of the any kind of a move, or you can say body movements. So it will always produce a signal with some kind of artifacts. So therefore, we must check the quality of the signal before transmitting, before processing, for extracting the parameters. Then communicate, as I explained, we will provide a network coverage. We will ensure the communications network, the reliability of the communication. Aggregate is very simple. We can say I just create a data. I aggregated data, but who is going to develop something is called edge AI intelligence system, or we can say edge AI inference engine. That means it's going to process a large amount of data to diagnose some kind of a specific type of diseases. So these are the set of wireless technologies that we must know. Then assuming that we have developed a Internet of Things framework for health monitoring applications, we also assume that we have perfect communications, and also we have perfect network coverage. So with this, we must also know the different categories of IoT. Which part of the IoT we want to work? It's called trackable object IoT and data object IoT, interactive object IoT, and smart object IoT. Each of this category of IoT has a different applications with a different challenges. If I know that, yes, I am going to work with interactive object IoT framework, then I must know the definitions, then I must know what are the challenges. But one cannot say that whatever I developed IoT framework for a particular trackable, which can be extended for a interactive object IoT. For example, I developed a IoT network for sensing air quality parameters or water quality parameters. But we cannot blindly adapt this one for a sensing a what is called vital signs from the human body, because it has a different sampling rate. Okay, it has a different sampling rate, which has a different data rate. So that we must know what will be the sampling rate, how much data from each of the sensor. If I gather all kinds of data, what will be the total volume of the data or total amount of data that need to be transmitted? Then I must choose a specific type of what is called wireless radio. Now, if I say specific type of wireless radio, if I am going to do predictions with the support of a edge computing platform, or with the support of a cloud computing platform, then I must choose a long distance or a short distance and or medium distance, or we can say short range, medium range, long range wireless radios. So by selecting this way, we can reduce the overall energy consumptions. If I select a short range for what is called performing any kind of feature extraction with the edge devices. Let us take a laptop. I have a smartphone, so my wearable devices can interact with the smartphone, which with the support of a short range wireless radio, it can reduce the overall energy consumption. So therefore, we must know that which part of the IoT category we want to aim or we want to do solve it. So these are different type of use cases of IoT, but we are mainly focusing with the healthcare. So then we must know what will be the IoT model. Let us take for health monitoring. I will say Internet of Health Things, Internet of Medical Things. Sometimes they are saying the medical Internet of Things. Sometimes they say Internet of Bio Nano Things. So you can see slight variations in the title, but each of these use cases, the model will be different. The architecture will be different because the sampling rate will be different. The functionality in terms of extracting the parameter will be different. The functionality in terms of a fusion of the sensor will be different. So therefore, even we feel that it's a small variations in the title, but one has to propose what is called efficient IoT architectures. Efficient IoT architectures by considering the different kinds of layers. So now I grouped this type of problems based on with reference to connected devices, connected system, because here also we must know that when I say subject to home, it will have different challenges. When I say home to hospital data transmission, it will be different. It will have different challenges. Ambulance to hospital, hospital to hospital, hospital to ambulance, subject to caregiver, and diagnostic lab to hospital. So we must know that which part of this circle I want to work in the case of AI-based health prediction, because each circle it requires a different, the requirements will be different, and also the challenges will be different. Again, this is just a framework. He published a paper just saying that intelligence in the Internet of Medical Things era, a systematic review of current and future trends. But it's all simple diagram. If you just consider any one of the sensor, there are n number of challenges because of miniaturization of a sensor, which can produce a bad quality of the signals in the different activity conditions. It can be under ambulatory conditions, you will find a distorted signals. The wrist PPG will, or we can say wrist watch will produce a noisy PPG signal, or we can say wrist PPG will have more noises, severe noises and artifacts as compared to what is called a traditional fingertip based PPG. Now, but I cannot use a fingertip PPG for every day, every time. But I can use only wrist PPG, wrist watches. But it cannot be, it cannot produce a high quality PPG signal under different activity conditions. So how do you solve this problem? Is there a way to what is called providing intelligence to the deep learning network or AI system? How do you say that this AI-based system means know that the signal is connected to the noises and artifacts? So if I do not have this framework, then I cannot be good data scientist. It's not that blindly I'll create a model, or sorry, blindly I create a signals in a closed environment. I created a model. Then if I deploy that model in a different recording conditions, then I will not get a good accuracy. I may get good accuracy for the same recording conditions, but under different recording conditions, and then I can see more number of, or you can see more false positives or false alarms. Now, this is called intelligence to the AI. So therefore, I always take the AI is automation and intelligence separately. We are using a deep neural network for automating a process of extracting the parameters. That is also a challenging problem. But we are using a contextual information combined with a deep neural network. We will provide intelligent protocols or intelligent features to the existing accurate estimation of the parameters to improve the diagnostic relevances and accuracies. So that's very important. This is just a diagram, but there are a number of problems that need to be addressed, even if you take any one smart, what is called devices here. Now we must know what type of sensing nodes you want to develop. Do you want to develop the implant sensing node, body surface sensing node, contactless or external sensing node? Now, why do you want to know all this sensing node? Because I purchased sensing node from somebody, but I am just collecting a biomedical signal. Let us take, you want to measure the pulse rate. You will find a n number of papers. They say that pulse rate using ECG signal. They say pulse rate using or heart rate by using a PPG signal. Somebody use a seismocardiogram. Use to study a function of the heart by using ballistocardiogram. Somebody use a contact sensor to study the function of the heart. Somebody use a non-conductive sensor to study the function of the or we can say health of the, to monitor health of the infant and elderly people. Now each of this type of sensing mechanisms will have a different kinds of noises and artifacts, and will have a different kinds of clinical parameters. If I take a PPG sensor to measure only the pulse rate, then I can get some more information about the heart functionality. But if I try to measure the pulse rate by using a contactless sensor, sometimes we are saying visual based or RGB camera based what is called pulse rate estimation. I can get the pulse rate estimation, but I cannot use such a signal for further, or we can say further diagnosis of various kinds of cardiovascular disease. So now each of this sensing mechanism, if it is a contact, it will have different types of noises and artifacts, and also it will have a different kinds of clinical information in the sensed signal. If I take a contactless, maybe it is ease of sensing. It's more comfortable for an infant and elderly people health monitoring, or any kind of injured patient health monitoring, but it will have a different clinical information, and it will induce a different kinds of noises and artifacts. So therefore, we must know what type of sensing category or sensing mechanism that will be adopted when you want to develop AI. If that AI platform, when you say that AI assisted healthcare devices, where this type of information is not embedded, then we cannot say it's called intelligent, because otherwise it will produce more false alarm. Now, this is also very important. When you say for accurate and reliable event monitoring using deep learning networks, we must know what type of strategies that we are going to follow in terms of acquisitions, contact, and contactless. Sensing strategy, is it a periodic or a continuous? A data computing strategy, or we can say that the parameters are extracted on a device, parameters are extracted on a portable devices like a smartphone also, or the parameters are extracted in a home-centric computing system, or the parameters are extracted cloud computing system. So now, why do you want to know these type of strategies? Because again, the challenges are different. If I say that I want to measure vital sign on a device level instead of a edge level or a cloud computing, then I must consider the resource constraint. If the device is affordable or a low cost, then we must know that it have a limited computational power and limited battery capacity. So then we have to design a lightweight deep learning networks or a lightweight signal processing techniques to extract the pulse rate from a PPG signal. But if I say that that is estimated on at the edge or at the cloud, then I must ensure the communication network. I should ensure the network coverage. If I do this type of estimation on a device, I can provide a intelligence to the user, and without expecting the network coverage, or without what is called having any kind of what is called communication failure. So therefore, we must know that different strategies that will be adapted for computing, different strategies that will be adapted for sensing, different strategies that will be adapted for acquisitions, different strategies that will be adapted for decision making, different strategies to get the information of your contextual data. Now, when you say that cloud and edge computing, what are the advantages that we can have when you do the computation on edge level and devices? We can have more benefits in terms of user privacy and the security, and we can have no latency, because no network is involved here for transmission of the data, because all the parameters are extracted on device level. Then it will solve the problem of communication failure, which is a common problem when you go by train and still your wristband, if you say that is connected with the 2G or 5G networks or a 3G networks, you will see a communication failure. At the time of communication failure, how do you get this type of machine information at the what is called server level or at the cloud-based diagnostics? So now that's very important. How do you provide a network coverage? Then we can reduce the bandwidth utilization cost, and edge computing will not demand high bandwidth in wireless radio, and also it can reduce the cost of the device, and it will reduce the treatment cost, because we can do some kind of abnormality detections at the device level. We are not going to continuously process the normal signals. We will process only a signal which are having a different patterns as compared to the previous patterns. So these are called intelligent protocols that can be incorporated with the wireless communication networks, or you can say AI-based system. Then we can reduce the energy consumptions, because most of the energy consumptions at the time of transmission. Now, what is artificial intelligence? Why that is so important? So, not just a machine learning. That means what? I'm going to extract. I'm going to classify a signal. Okay, I want to detect specific type of arrhythmias. Nowadays, what is happening? That is putting a traditional machine learning classifier. Still, they say that AI-based system. There is no AI. Or even if I use a deep learning to detect a specific type of arrhythmias, that's not a AI. Okay, AI in the sense we have to put intelligence to the automatic process. I can use deep neural network to what is called improve the accuracy of a pattern classification, or we can say improve the accuracy of cardiac arrhythmia classifications or any kind of abnormal detection system. But I must also embed the contextual information that is called intelligence that can improve the diagnostic relevances and accuracy. So contextual information is very important, and simple what is called deep neural network learning process, and it cannot be a what is called AI-based system, or we can say deep neural network learning and also IoT can empower the AI-based system by providing various of data. Now we must also know what type of AI that we want to address. It's not that whatever I developed a system based on SVM or deep neural network, we cannot called that is AI-based health monitoring. Okay, so there is some kind of a definition. One is called strong AI, weak AI. Within that, we have some kind of a classification is called artificial narrow intelligence, artificial general intelligence, artificial super intelligence. So now, which part of the AI we want to work? These are the examples. So now, whatever the rule-based system, which can help us to automate the process of detecting and what is called making some kind of a decision, it is called narrow intelligence. Okay, that means we should know this type of framework. That is something is called rule based, and then we can say that closed domain, open domain, retrieving responses, generating responses. So we have something is called rule based and impossible general AI, that is called generative AI, then intelligent machines. Now you can understand the complexity of this framework. Which part of the quadrant, or you can say which part of this what is called do we want to have a generalized, or you can say generative AI or intelligent machines, rule-based machines? Impossible. So most of the cases we are developing a systems based on the rule-based, which is not AI. It is going to give some. It's going to solve specific type of problems, but it cannot give a perfect solutions when there is a queries from the out of this training process. So therefore, we must know what type of AI that we are going to solve it. So now, when I say that I'm going to replace the traditional machine learning with the deep learning, sometimes we'll say that deep learning is a black box. It's not exactly black box, but we must know that there is some correlations between the traditional machine learning process and the deep learning feature extraction techniques. Or we can say deep learning networks can be used for extracting the features, or we can say that the deep learning can be directly used for detecting or classifying any kind of events. Now, some of the research group, they use a deep learning networks to produce a features, and then that features will be trained with any kind of a traditional machine learning classifier. Now, what are the building blocks or functional blocks of a traditional machine learning? So we will have we will have a pre-processing, we will have feature extractions, and then classifier. Okay. Now the pre-processing is to perform some kind of a what is called noise removal or amplitude normalizations or mean subtractions. So, and also we have feature extraction. We'll extract a specific type of features based on our expert or subject knowledge. So I can do the feature extraction in the time domain. I can do the feature extraction in the frequency domain, or I can do the feature extraction in the time frequency domain, or I can extract the statistical features either in the time domain or in the transform domain, or you can say in the frequency domain or time frequency domain. So these are my subject knowledge. Yes, these are the type of signals that I want to process. I know the what is called spectral characteristics of this type of signal. Then I'll choose a suitable signal feature extraction techniques based on my subject knowledge, which will be a more accurate and reliable. There is no need to explain because it's well proven concept. So we can adapt. But nowadays, we want to say that, yes, there are few cases we may not get better accuracy because sometimes the fine detailed features were smoothed in the smooth in the traditional feature extraction techniques. So therefore, we will give a raw signal or raw images, or we can give a transformed signal in terms of a spectrogram, MEL spectrum to the deep neural network. We expect that the fine details will be captured in such that two closest what is called patterns can be accurately classified, or two closest events in terms of a small variation in the frequency, but the different kinds of arrhythmias that can be detected accurately if I can train the same data with a deep neural network. That is the our assumption. Now, if we take this type of feature extractions, now we are going to use a conventional layers. If we look at the building blocks of the what is called convolutional neural network, we will have a conventional layer which will perform a feature extractions. Now we will have a pooling layer also. What is the function of the pooling layer? It is a subsampling stage, or we can say that it's a feature map reduction stage. We will use either what is called mean pooling or max pooling, sometimes average pooling. Now you can also see a traditional machine learning based system. They will also use something is called feature reductions or dimensional reductions. Now we have patch normalizations, we have dropout. Now you can easily correlate different types of functional blocks which are adopted with the traditional machine learning is also followed here, but it runs with a closed loop. It tries to produce the best model, but it takes more time without much intervention of a researcher or any kinds of individual. So we are expecting that the feature will be generated, but we do not know what type of features are generated, but still I can have a better accuracy, but the model size will be large. So how do you implement such a large model and a limited or you can say resource constraint variable devices? That will be challenging if I solve the problems with the convolutional neural network or deep learning neural network. Now, how do you solve it? I'll show one of the examples how to do it. Now, we must also know big data analytics because that is based on the different V. So this is the few number of, we started with the 3V, but this is the big data analytics definitions based on 10 Vs. Now, each of the V has some meaningful information. We can also introduce one more V, we can say 11 Vs, but we have to define what is the use of each of the V. Now, if I know how to collect the data by using IoT platform with the contextual sensors and also a physiological sensor, now I must know what type of analytics that I want to perform for a specific type of applications, particularly health monitoring. If I do not know this type of data analytics, I cannot provide innovative solutions in terms of what is called reduced false alarms, energy consumptions, and with the improvement of accuracy and reliability. Now I want to work with the descriptive analytics. Now, what do you mean by descriptive analytics? Aims to answer the question what happened over a given period of time. Now I have a wristwatch and it can display the pulse rate. If the pulse rate is greater than 100 beats per minute, now it's called a tachycardia. Pulse rate is below 60 per minute, it is called bradycardia. Now in this case, something happened in my heart, okay, that can be observed based on the pulse rate. Now this problem means this problem is what? Accurately estimating the pulse rate or accurately estimating the heart rate. Now it will have a different challenges and different requirements in terms of the sensor. So it summarizes the large data sets to describe outcomes using specialized metrics and requires a collection of relevant data. That's very important. Here I want to measure the pulse rate. Now I have to, if I want to validate my pulse rate estimator or a measurement techniques, I should collect a variety of data from infant to adult. Okay, or you can say elderly people, not adult, infant to elderly people, but still I have to consider different age group and the gender and different geographical locations and different kinds of arrhythmia abnormalities. Then I can say that my techniques can accurately estimate the pulse rate parameter that indicates something happened to my heart. Now, I want to work with the diagnostic analytics. I'm not going to work with the descriptive analytics. I assume that there is something very good system. That means wristwatch is producing nowadays accurate under resting condition. With that assumption, I want to solve the problems of diagnostic analytics. So what do you mean diagnostic analytics? Helps answer questions more on why something happened. Now my heart rate is increased, heart rate is decreased. Is it due to the physical activity? Is it due to the emotional states? Or it can be a stress, or it's due to the environment under heavy pollutants, extreme heat, extreme cold, or it's due to the defects of the heart or any malfunctioning of the heart chambers. Now, this is called why something happened. Now, what I highlighted that contextual information in terms of physical activity and emotional states and extreme weather conditions or pollutants, then the physiological defects. Now, finding a descriptive analytics and digging deeper to find a causes. That's very important. Then if I say that I'm going to work with the diagnostic analytics, now a variety of sensors need to be used. In addition to physiological sensor, I must have accelerometers to know the human activity. I must have a air pollutant sensor or a environmental sensors to get the all the environmental information, climate information, which also impact the variation of the heart rate. Now that is called why something happened. Now this complexity is different. If I do not know the definition of this, I cannot solve. Yeah, this can be a good data scientist. He must know, yes, what are the different type of sensor that need to be used for diagnostic analytics. How do you collect that type of data, variety of data, and what are the different type of noises, artifacts I can see. Okay, for this type of heterogeneous sensor, then that is most important for developing we can say that reliable, trustworthy diagnostic analytics. Then predictive analytics is the next research problem that yes, I am not going to work with the descriptive analytics and diagnostic analytics, but I want to work with the predictive analytics. As I mentioned, I want to predict ventricular fibrillations, or we can say arterial fibrillations. Now, helps answer questions about what will happen in the future. If I forget to diagnose heart rate variability, or we can say forget to diagnose a tachycardia or a diagnosis of bradycardia, what will happen if the tachycardia event persists for another 1 day or 2 days? Or if I do not timely treat a ventricular tachycardia, what will happen to the heart next? It may be ventricular fibrillations. Now, if the ventricular fibrillation is not treated timely, then what will happen? So you will find that heart chamber or particular ventricular chamber cannot pump the blood to the rest of the body. Then you can see what will be the future. So therefore, we must know what will happen in the future if that type of events is not treated properly. That need a historical data. Now, descriptive analytics and diagnostic analytics may not record a historical data, but when I say that I'm going to work with the predictive analytics, who is going to provide the historical data for a specific type of organs, n number of organs in the human body. With the different age group, different gender, different geographical locations, I need to collect a historical cardiovascular data. Who is going to do? If I get a historical cardiac data, most of the time it will be unstructured data. Now, what are the tools that need to be convert that unstructured into structured? Then what are the patterns that need to be captured that also demand different kind of deep learning networks or any kind of tools? So these are the different challenges that need to be considered. Now, what do you mean prescriptive analytics? So it helps answer to your questions, what course of action that need to be taken. So that's very important. Yeah, 1 minute. Yeah. So now you can understand in one slide itself, we can understand the complexity of the problem that need to be solved when we say that AI-based system. But one cannot provide a solutions for this type of all 4 types of analytics. I choose descriptive analytics. I'll try to solve the problems. Okay. Then diagnostic analytics will have a different complexities in terms of research challenges and the type of sensors. Subject knowledges also will be different. Or we can say expert knowledge also will be different. Then the requirement also will be different in terms of computing. Then the amount of data that need to be collected, and that's also will be different. Then predictive analytics is a completely different that we should have a historical data. Without that, we cannot do. Then prescriptive analytics helps answer questions about a course of actions that will have a different insights from your predictive analytics. Data-driven decisions can be made, and by analyzing fast decisions and events, the likelihood of a different outcomes can be estimated. Who is going to store the fast decisions or events of a particular person? So that's also very important. How accurately you can, sir, how much you can securely say secure the such a decisions, or somebody can what is called alter the informations if it is connected with the internet. Now the question is that what is the science in the data and who can be an intelligent data scientist? Because nowadays, so we started many data science departments and many of offering different courses. But I just want to highlight that if I want to work with the what is called AI-based health monitoring system or AI-based healthcare system, then I want to say that I can be a intelligent data science in the sense I must know what are the different type of signals. So in the signal acquisition itself, we should know, is it a unimodal signal or a bimodal signal or a multimodal signal? Is it a single channel, multi-channel, or I can solve this problem by using multi-model signals with a single channel information, or I can use a multi-channel for a single model by improving the quality of the signals. Then we can improve the accuracy and reliability. Or I can choose a suitable sampling rate. So now that sampling rate selection is based on the type of parameters that need to be extracted. Or I can use a new data acquisition strategy, which is called compress sensing. Now, if I want to use compress sensing, is it possible to extract all the vital sign parameters in the compressed domain without using a computationally expensive reconstruction algorithm? So these are the most intelligent part of the system. If I do not know this type of what is called science or informations, and before starting AI-based healthcare system, then I cannot be an intelligent data scientist. Otherwise, we are simply, we'll download the database, we'll integrate with all deep learning networks, we'll also get some more accuracy, 99 or 98, which may not be useful for any kind of a practical applications. If I cannot explain that, yes, this false alarm can be reduced if I can check the quality of the signals. So this is another confusion, what is called chart, or we can say what is called design diagram, where we use physiological signals for diagnostic application. We use a physiological signal to understand the physical activity. You will find some of the research group, they use a physiological signal to understand the physical activity without use of accelerometers or additional sensor. They use a physiological signal for emotion recognition. They use a physiological signal for biometric recognition. Now, if I say that it's going to be used for biometric recognition, I must ensure that whether the subject is normal or abnormal. Okay. Otherwise, I cannot say that. So, or if I'm not incorporating this physiological signal feature extraction, then we cannot say that this can be used for biometric recognition. Then emotion also, the emotional state recognitions may be based on the biomedical signals, may be more accurate. It may be relevant if it is a normal subject. But if there is an abnormal subject in terms of the defects of the heart or in terms of the defects of any neurological disorders, then we cannot say that what are the emotional recognitions that we got, emotional state, may be accurate in term for a pathological cases. Now, physical activity can be recognized by using a physiological signal, assuming that if the signal is corrupted with the noises and artifacts, we assume that I'm performing some kind of physical activity like a movement of the hands. Therefore, the signal is corrupted with the what is called movements, or you can say corrupted with the any kind of movement artifacts. If I can see a movement artifact signal, I can say that the person is performing some activities. But sometimes it has challenges. If the pattern changes also due to the defects of the heart, then it's difficult to know that whether that detection is reliable or accurate. So now, if we say physical activity recognitions, without fusing a physical activity recognitions, we cannot do the diagnosis of a pulse rate when we collect from a remote persons. If we are visiting the hospital, your pulse rate or vital signs are measured under controlled environment or a bedside monitoring. So there you are the what is called resting condition. Under resting condition, we are extracting the parameters. That information is available to the doctor and the diagnostic system. Particularly, it's a bedside monitoring. But if I say that I am going to design a system which can enable a remote health monitoring by using AI-based health devices, then we must ensure the physical activity information. We must ensure the emotional, or you can see that a person can give a data while drinking alcohol or consuming some kind of drugs or smoking. That also will change the patterns of the signal. So therefore, this is very interesting functional diagram with so much confusions. Then we can decide that if I do not have such a knowledge, then I cannot do best science, or in terms of I can say intelligent data science. So this is another interesting part that I want to do what is called cardiac arrhythmia recognition system development based on the deep neural network. I can just collect a variety of signals, which is, or we can say I can download the database which is available in PhysioNet. I can do this type of classifications: normal, supraventricular, ectopic, fusion, ventricular ectopic, and unknown. So which is very simple. And we can see many research groups published more than 1 lakh paper, we can see based on the same database. but it is not useful for many of the applications because here we are mainly focusing on the cardiac arrhythmias. The arrhythmia is defined in terms of regular patterns, irregular patterns, and a heartbeat. It can be a slow heartbeat, fast heartbeat, normal heartbeat. Now, within this regular patterns of what is called regular heart patterns, you can have a tachycardia, bradycardia, and normal. In irregular, you can have a different varying heart rates and also a different morphological patterns. So now, if I am not following this type of stage-wise classifications, I cannot able to develop a system, unique system or unified system, can able to recognize a variety of arrhythmias which are reported by the doctors or clinical studies. Otherwise, I will just end up with a normal and group of what is called cardiac arrhythmias based on the QRS complex patterns or morphological patterns. We assume that that can be captured by the temporal DNN or some kind of a spectral DNN and CNN network. But if I apply my fundamental subject knowledge, yes, I'll do this two-step, multi-stage development system, multi-stage system development. Like a first stage is it is a what is called regular, irregular. Then within the irregular, I'll perform it is a what is called slow heart rate. It's called bradycardia. Then we'll have tachycardia. Now we have different types of arterial. Also, we can have tachycardia. We can have ventricular tachycardia also. So there are different kinds of tachycardia that can be diagnosed, and different variety of arrhythmias can be recognized if you follow this type of architecture. It's called unified architecture with the multiple stages. Okay, that is called heart rate classification, rhythm recognition, then the arrhythmia recognitions based on by fusing heart rate what is called heart rate heartbeats informations and heart rhythm informations and the shape of the P wave, QRS complex, and the T wave. So all these things are very important that whatever we develop, okay, it should follow the patient safety, ethics, governance, and data bias and drift and data security. That's very important. So then there are something principles and recommendations for AI-enabled healthcare. So I taken from World Health Organization with the reference to robotic surgery, but still extended for any kind of this. It should be useful and it should be safe and accountable and transparent, explainable and interpretable, and it should be fair with the harmful bias managed and secure and resilient and privacy enhanced. That's very important. And also it should be inclusive. Very important that AI for health can be designed to encourage the widest possible appropriate, equitable use and access, and irrespective of age, sex, gender, income, race, ethnicity, sexual orientations, and ability or other characteristics protected under human rights codes. That's very important. That means called reaching the sustainable development goals. So that's very important. Otherwise, we have to have 5 A's. That's called accessibility, okay, availability, okay. So these are the very, very important what is called recommendations we should consider when you develop any kind of AI-based system. In the sense, I should not say that I will develop a system which can collect data from an internet source and to create a model, then it will lead to a wrong diagnosis, because who is going to validate that comes from the internet world, whether that data is relevant for a cardiovascular disease or that data is irrelevant, whether that data is corrupted with the noises or artifacts. So this is one of our framework that we proposed Internet of Medical Things reference model for smart health monitoring with the different kinds of layers. And then we must also ensure the security and privacy. There is a patient level security, device level security, then data security and institutional level security. Each of the level will have a different complexity. That's why I highlighted here that, yes, I'm going to solve with the patient's security, or I am going to solve the problems of a device security or a data security and institution security. Now, in all these cases, when you say that I'm going to develop AI-based, that means we are aiming for a prediction of a various kinds of abnormalities. When you say a prediction, that leads to a continuous sensing, processing, and transmission of your data. Or I can say continuous sensing and processing, and then triggering the external devices. Now, continuous sensing and processing incurs so much energy, or we can say incurs huge amount of energy consumption, because the sensors are operating with a different sampling rate. Most of the times, it's a higher sampling rate as compared to air quality parameters. It may be one samples per second or one samples per minute, or temperature, it can be one samples per second or one samples per minute. But when you say PPG signal, EEG signal, EMG signal, or electrocardiogram, say, or we can say seismocardiogram, electroencephalogram, it operates in a different sampling rate. So now it can increase the energy consumption at the sensor level, at the processing level. Is there way to reduce the overall energy consumption? Yes, there are n number of ways or n number of strategies that can be adopted to reduce the overall energy consumption. One is called compression sink based architectures, or compression sink based compression sink strategy, or exploring lightweight deep learning models, and developing a energy efficient or we can say parameter extraction in a compressed sensing domain, and incorporating the quality aware event triggered communication protocols, and also enabling noise aware signal denoising and protocol, and also having a quality aware data compression. So by adopting this type of intelligent signal processing protocols, we can reduce the overall energy consumption, in addition to exploring different kinds of energy harvesters based on the 4 ambient energy sources like solar, kinetic, and heat. Then whatever the movement we got, I have listed here. Yeah. So we can, so in addition to this 4 type of ambient source based energy harvester, we can reduce the overall energy consumptions by exploring a lightweight, what is called sensing protocol, lightweight processing protocol, either by using a traditional signal processing techniques or a deep learning networks. So here I want to highlight that this is the standard database used for evaluating our proposed methods. So here I want to highlight the importance of this biosignal quality assessment. So you can see the signal without noises and artifacts. It will have wide QRS complex and narrow QRS complex. So this is the signals corrupted with the electrode movement artifacts. This is the signals corrupted with the muscle artifacts, some portion of the muscle artifacts, but this is the signals corrupted with the entire portion of the muscle artifacts. Now I can incorporate some kind of intelligence to check the quality of the signal before extracting the parameters, because if I extract the parameters from the noisy signals, it can provide a unreliable measurements. Sometimes noise also can provide a pulse rate, because the noise can mimic a similar patterns of the ECG signal, which can produce a what is called a pulse rate, which can be a normal, abnormal, or it can be a tachycardia, bradycardia, normal. But that measurement is done. That measurement is from a noisy data. So we must check the quality of the signal before extracting the parameters, or before before detecting any kind of abnormalities by using a deep learning network. So that means what? My deep learning should have a pre-processing of checking the quality of the signal. That's very important. Now, if I take this example, that this is the electrocardiogram signal corrupted with the muscle artifacts in some portion. Okay. So now, instead of completely discarding the this ECG signal, I will detect what is called presence of the noise. Then I will locate to the, or I can find the start and end, starting time and ending time, or we can say that boundaries of the muscle artifacts by using simple signal processing techniques. Now, once we know the starting and end of this muscle artifacts, then we'll discard that muscle artifacts portions from this. That means I'm going to miss some amount of data. But sometimes we can assume that this smaller amount, I can just embed it with the present data or the future, or in this case, previous portions or the next portion of the signal. But or I can apply a denoising only on this noisy data. Instead of blindly applying a denoising on the entire portion of the ECG signal, that may distort my SARF QRS complex. But by doing this way, I can preserve the SARF QRS complex for a noise-free portions. Then still I can remove some muscle artifacts with the distortion of minimal distortion in a QRS complex. So in this way, we can also develop a noise over denoising framework, which can reduce the overall energy consumption and also ensure that preservation of the diagnostic information for the deep learning networks, which is explained here. And these are the devices commercially available, but still in the risk cases, by using a deep learning also, we can have what is called poor accuracy in terms of estimating the pulse rate. You can see the pulse rate error is 10 beats per minute, which is not acceptable by American Heart Association. It should be minimum what is called error of 5 we can say 5 beats per minute. But all these things are mean absolute error. So mean absolute error is not a right metrics to validate the performance of this type of devices. We should have a estimation error range, in the sense the number of segments, okay, within that error range, number of segments with the zero error, number of segment with the error from 0 to 1, number of segment with the error from 1 to 2, then that accumulation of the informations can be best metrics to validate the performance of this. Otherwise, the mean absolute error, it's a simple metrics which cannot be useful for this. And also from this table, and we can see that for just estimating the pulse rate parameters, they need to store 60 million, or we can say, sorry, 60 into 10 power 6 parameters need to be stored. That means how much memory is required. But this task can be done with a traditional signal processing auto, but it will time-consuming task. I should be expert in this domain. But you can see it demands a large models, but it consumes so much energy, because while estimating the pulse rate, we have to read 60 into 10 power 6 parameters. So if you assume that if one parameter reading is 1 nanojoule also, and then still it is a 1 nano into 60 into 10 power 6. So still it consumes so much energy for just for reading a data. Okay, reading a parameters. So that means reading a parameters in most of this computation, or we can say largest deep learning model, will consume so much energy. Therefore, we need to explore a lightweight model. So this is the one example I want to demonstrate is a single signal processing techniques or feature is sufficient to detect VTVF, but that requires a fundamental subject knowledge. So here I can show the ECG signal. You can see the different kinds of ECG signal. These two are ventricular tachycardia, and this is the ventricular fibrillation. These are non-VTVF. Now, if I see the non-VTVF, I can observe some information that we have isoelectric segment, which is very close to 0. And here there is some isoelectric, not much long isoelectric segment close to 0. Then if I inject some kind of noises to this type of signals, I can separate this VTVF from a non-VTVF. So this is studied with, by using a standard database. Then I extracted zero crossing rate, and here we have plotted for visual inspection of the what is called performance of zero crossing rate feature. That means with this feature, we cannot accurately detect a VTVF from non-VTVF. Now, after injecting the noises, then adding the, then extracting the EZCR, I can able to separate a VTVF from a non-VTVF. It's a simple feature extraction technique, simple feature, which is a zero crossing rate measurement, which can be done in the time domain, but I'm injecting the noises because I have some subject knowledge. If I do not have that subject knowledge, I have to just collect a variety of VTVF, non-VTVF. I can blindly combine with the deep learning. But who is going to provide a wide variety of VTVF for a different kinds of subjects, age groups? Who is going to provide a variety of other non-VTVF events? So that's a challenging problem. But in this case, I don't want to have much complexity in creating such a databases like a VTVF. 5 minutes. Yeah. So this cases, so we are just extracting the zero crossing rate. Then based on this, we can classify or we can detect VTVF, but it is simple time domain feature extraction techniques, and it is only zero crossing rate. So to prove this one, we also what is called created a model with a convolutional neural network with filtering and without filtering to show that improvements of the accuracy in terms of a filtered ECG signal. Then we have observed that yes, the filtered ECG signal can improve the accuracy, but still the model size is very large as compared to a single feature based VTVF detection, which I shown in the previous slide. So this is the way we can justify, yes, for this application, a single feature is sufficient, which is most important because VTVF is always the detection algorithm protocol will be embedded with what is called external defibrillator. Okay, that's also a resource constrained device. So where if I use deep learning model, that itself consumes more energy, but we need to have that external defibrillator or for a longer durations with a one-time charging. So therefore, we have to explore a simple feature based or lightweight V2F detection that we have demonstrated by using a standard database. So these are the results, and I can just open for the questions. If you have any doubts, you can have the discussion now. Hello. Hello.
Participants, thank you, sir. Thank you for your wonderful session. In spite of your busy schedule, given this wonderful lecture, sir, it is very informative and knowledgeable. Participants, any questions, you can chat or you can ask by unmuting yourself. Participants, any questions?
Okay. Any questions from the participants? If there is no questions, thank you for attending the session. Yeah.
Any questions? Participants.
Okay, thank you. I think there is no question.
Purna, Shankar to everyone. You can give your feedback. Yes, you can talk Lakshman Perika. Thank you, sir. Session is very informative, sir. Thank you.
Yeah, thank you. Thank you for attending this session. So yeah.
Sir, one question, sir, from Muhammad Faisal.
Hmm.
How the disease management which support IoT-enabled health intelligence
So
network box intelligence?
see, we try to use IoT platform to collect a heterogeneous data, which is very important for predicting any kind of diseases. That's why I taken the example of pulse rate. You have wristwatch, which can accurately estimate the pulse rate. But if that pulse rate is not embedded with the other contextual information, but for sensing the contextual information, I cannot put additional sensor to the wristband. So nobody will buy because it will be bulky. So now I'll use the internet protocol because I assume that I'm in a location of a Palakkad. I know weather conditions, so I can get the data from this. So this is called the way where we try to use intelligent IoT platform. It can provide a heterogeneous data, which is very important, which is always for embedding the contextual informations or healthcare application. But I'm giving a SPO2 level, but I'm staying in a Ooty or somewhere Himalaya. Then my rate will be different, obviously, because of the different altitude. So that's why we have to know geographical locations. Who is going to provide this geographical location? I cannot put a GPS with a wristband. So then we are trying to, we can say it's a concept of crowdsourcing also. We are trying to use the existing framework, but still my existing device can interact with the other devices which are enabled or implemented by other groups also. So in that way, we use IoT based. That's why I mentioned that IoT empowers AI based system. Okay, because when they design IoT, and the most of the industries they did not find a correct application. But when this AI based systems or deep learning based systems are introduced, and particularly prediction analytics, then they showed that, demonstrated that yes, this is the real world applications, because a platform should handle heterogeneous data with the variety of or we can say heterogeneous sensors with any kind of short range, or we can say two short range communication network, or mixer of a short range, medium range, that depends upon the distance between the cloud and the user. So which are the lightweight models, how to evaluate them? So that lightweight model is evaluated in terms of energy consumption. Okay, how much is energy consumption? Because when I say that, I take an example of a defibrillator. I have seen many people are working deep learning based VTVF detection, but that may not be useful for a defibrillator because that is a resource constraint. So one can argue here, no, I can buy a good defibrillator for 1 crore or a 10 lakhs or 1 lakh or a 50,000. Still, I can have a high speed processor and a limit, but at the end of the day, you will have limited capacity, battery capacity. But and also we have to ensure that whatever the technology that will be developed, it should be upgradable. So if I take a upgradable or a cost effective, I will have a limited resources. Within that limited resources with the cost effective of the device, I should look for a lightweight. I cannot put a deep learning model which takes 1 second to detect a VTVF before I have to apply electric shock also. No? So we have to know that how much latency that need to be given. So therefore, we have to look for a lightweight in terms of a energy consumption, in terms of a latency. That depends upon the application. There is no other metrics, only energy consumption and latency and model size. You can refer our papers. We highlighted all this model size and number of parameters, latency, memory size, and energy consumption. Most of the times we implement a deep learning on a RPI model. We'll calculate this, all this, we'll perform this type of energy consumption analysis. We use Arduino Dual also for measuring the all vital signs. If I'm not using a, or if we do not use deep learning. Okay, in this way to capture the chemical reactions of your medicines in our body, which model that I don't know much knowledge because what type of chemicals you want to observe, because everything is induced with the electrocardiogram or electroencephalogram. It's relevant to that. But for EEG data capturing, suggest which sensors are available. I can share this slide because I just recently presented one talk on EEG based, particularly wireless EEG based brain computer interface. I can share to the, in one of the slide, I added all the commercially available wireless EEG sensors with a single channel, multi-channel. I'll share the slide to the coordinator. You can contact them. So Parkinson's disease suggests which sensors are. So nowadays you can use single channel EEG sensor. So it is also commercially available, but very costly. But to study research study purpose, you can use it. And I will share that slide. Okay, set up. I have slides where we can see a single channel EEG sensor in wireless, particularly with the dry electrodes and wet electrodes. Yeah. For a diabetes, we should have a non-invasive glucose sensor, which is most important, which is also challenging problem. But some of the commercially available non-invasive glucose sensor uses the multiple PPG sensors, the different wavelength. But still, we have to conduct more studies whether to know the accuracy of this glucose level measurement by using PPG sensor. Yeah. So with this, thank you for attending my sessions, and you can email me if you have any doubts and if you want to get some database. Yeah, thank you.
Thank you very much, sir, for your wonderful session. Thank you, sir.
Yeah, thank you. Yeah.
Have a good day, sir. Thank you, sir.